will also be able to join. Please let me know if my screen is visible. Is my screen visible?
Yes, visible, sir.
Okay, so let's start from this place. I think this time is my pointer also visible, right? The red color pointer.
Yes, sir.
Okay, ठीक. So let me start from this place where we left. We were looking at how to solve a linear equation. Consider a linear equation ax equal to b, where both small a and small b are some constant, a scalar constant. Then, when a is not equal to 0, we can simply write x is equals to b by a or small a inverse b. There exists only a single solution. There is only one solution here. If a is equal to 0 and b is equal to 0, when both a and b are 0, then x can take any number of values. So that means x has infinite solution. So x can be 1, 2, 3, 4, doesn't matter, because a and b both are 0 and 0 equal to 0 is always satisfied for any value of x. Now, the interesting case becomes when a is actually equal to 0 and b is not equal to 0. That means when a is 0, whatever value of x you take, it will become 0 equal to b. And b is not equal to 0. That means that this does not satisfy. Therefore, any value of x will not satisfy this equation. Hence, no solution. So there are these three interesting cases. When a is not equal to 0, there exists exactly one solution. When a is equal to 0, there can be two possibilities. One, when b is equal to 0, that means there are infinite solutions, and when b is not equal to 0, there are no solution. So till this point, is it clear? Like a equal to 0, a is not equal to 0, there is only one solution, and when a equal to 0, then there are two possible cases. When b is 0, infinite solution, and b not equal to 0, then there is no solution. Is this two situation clear? Uh, okay, I will take it as yes, I guess. Please stop me if you are not able to follow, because today's lecture will be looking into where now this a and b's are in scalar form. Now, what if we turn into a matrix? We will look into those situations now. So, if this part is not clear, I will go again. But if this is okay, then I will go ahead with it. Okay, so I will assume it is okay. Please ask me again if you find it difficult to follow with matrices now. Okay, so these were the case, and we visited when we have more than one equation and more than one unknown. Then we have two x equals to. So there are two equations and two unknowns, x1 and x2, and there are two equations, and we can convert these equations into a matrix form. This is again a problem. This is 5 and minus 1, though, and we can actually write when a is not, we can also write x is equals to a inverse b as previously stated. So this we can write x is equals to a inverse b. So we can also convert a inverse of the matrix and calculate b. So we had this equation for a while, that we can convert matrix into linear equations into a matrix form, where 2, 3 are the uh, values of the equations, 2 and 3. 2x plus 3y is equals to 8, 2x plus 3y equals to 8, x minus y is equals to 8, and then we performed some row operations and converted into this form as we were doing in our high school math. And eventually, once we have this form, we can directly calculate the value of x. X is equals to 32 by 5, and similarly y is equals to, similarly you can put the value of x and calculate the value of y. So this method is called a Gauss elimination method. Now, this was what we left previously. As discussed previously, we will actually look into the calculation of A inverse matrix. Remember this A inverse that many of you were not familiar with how to calculate A inverse. So let's look into A inverse calculation then. Okay, so how do we calculate A inverse? We first calculate A inverse is equal to the cofactor calculation. So before looking into the A inverse calculation, we first need to understand how do we calculate cofactors. So for the time being, just assume that you need this cofactor calculation. How do we calculate? Is the focus is. Let's say C is a n by n matrix. C is a square matrix. Remember the last time we also said that A inverse can only be calculated for a square matrix. You cannot calculate A inverse in if the matrix size is not a square. For any general matrix, you cannot calculate A inverse. You can only calculate A inverse for a square matrix. So consider that C is a square matrix, n by n matrix. How do we calculate the cofactor? Just for the time being, assume that cofactor is needed. We will see how where is it needed. But let's calculate cofactor. How the cofactor is designed. Say for example, you want to calculate a cofactor at this position, C11 position. This position you want to calculate. So for example, so to calculate the cofactor, you need to remove the C11's row and C11's column. Oh, sorry, C11's row and C11's column, and whichever uh, shape of matrix is left, you calculate the determinant of this matrix. So by removing C11 row and C11 column, only this part of the matrix is left. So you calculate the determinant of this matrix. And the cofactor at this location is equal to, cofactor at position 1 comma 1 is equals to minus 1 to the power 2 1 plus 1 into the determinant. So this is how we define the cofactor. Okay. If you're not able to follow, wait for another example, and then we will take question here if there is any other doubt. So how about calculating a cofactor at C12? So you first remove this row and this column, and whatever matrix is remaining, C12, and combine these to C21, and here will be C23, and C2n. So this total matrix, we calculate the determinant of this combined matrix, and the cofactor at position 1 comma 2 is minus 1 to the power 1 plus 2 times the determinant. Now I will wait for a while to see if there are any doubts regarding this thing. Is this thing okay? Hello? If someone can say whether this is okay, not okay, I should repeat again. I should make another figure to explain. Am I audible in the first place? Uh, are people able? Are you able to follow this path, or is it going too fast? Can someone say something? Hello. I was not able to follow someone. Okay. I will just. Uh, okay. So please stop me if you're not able to follow. Otherwise, things will become complicated as we things will get more difficult and more advanced if you're not able to follow these. So please stop me if you're not able to follow. Okay.
Sure, sir.
Okay. Thank you again. Thank you again. So, I assume that there is no need to give any new example, or this, do you guys need a new example?
in this case section, or this is sufficiently clear that how to calculate cofactors. Okay, so let's assume that this is sufficiently clear and move ahead with the next set of thought. So why do we need cofactors? Remember the matrix inverse calculation? Say assume that you have a square matrix A which is defined as this. So the inverse of the matrix is 1 by the determinant of A and the cofactor at each of the instance transpose. So this is how the where the cofactor calculations comes in. So this for calculating the cofactor for previous slides were how to calculate these cofactors information. So this is how we define the A inverse. So as part of the previous exercise, did anyone was able to check whether A into this A inverse, if the A was this ABCD matrix, the last matrix, this matrix, did anyone check A if you multiply A with this A inverse, this value, we're able to get the same matrix identity matrix. If you have not tried it, then I will highly recommend try multiplying this matrix, A inverse matrix, with A matrix, which is A, B, C, D, and check whether you get the identity matrix or not. Because the idea of inverse was that you want to find such a matrix that if you multiply that matrix with the matrix A, it will give you an identity matrix. So this A inverse is defined as this in this square matrix case. So I highly recommend you multiply this matrix with A and see whether you get the identity matrix or not. So yeah, this is, I will leave you with an exercise again. So let's move forward. So today we will be actually be focusing into rank of a matrix, and this rank is very important. So what do I mean by rank is that if you perform some linear operations on row or column, if we can reduce the matrix into an identity matrix, then we call it as a full rank matrix. So let's look at this definition with example first. Consider that A is this matrix 1, 2, 2, 5. So that is 2 by 2 matrix it is, with 1, 2 as first row and 2, 5 as the second row. So if you perform a row operation, if you multiply this matrix, the above row by 2 and subtract this with the second row, you can get 0 and 1. Can everyone see that you can get A prime by multiplying the first row by 2 and subtracting it with the second row? And similarly, A double prime, you can get this value by multiplying the second row with 2 and subtracting it with the first row. So you get the A double prime. And hence you are able to reduce the A matrix by some row or column operation into an identity matrix. Hence A is a full rank matrix. So I will wait for a while to see whether everyone is able to follow this transition A to A double prime.
Sir, can we see the steps to derive the A double prime, A double matrix?
Okay. I haven't written any of these steps, but see this. If you multiply row 1 with
Yeah.
2, if you multiply row 1 with 2, so it will become 2. The first element will become 2, and the second element will become 4.
Correct.
And if you subtract the first row with the second row, so 2 minus 2 will become 0, and 5 minus 4 will become 1. So A prime, this is the first A prime.
Okay.
This
So
is,
4 minus 5, won't it be minus 1?
no, you're subtracting the first row with this, you're subtracting the second row with the first row. So you're just
reverse
subtracting
it
this.
is. Okay.
Okay. So this here is now what you do is that you multiply second row with 2 and subtract it with the first row.
Okay.
Can you see double prime now?
Got it now.
Okay. So if you can convert any matrix A into its identity form, you can call it as a full rank matrix.
Okay, sir.
Now,
Clear
okay. Now you actually don't have to go to identity form. Even just when you reach this location, you can say that A is the full rank matrix.
now.
Can you see why?
Because
As
you
the second row is in the almost 0 1 form. That's why.
exactly, yeah, because almost always, if the matrix is not just 2 by 2, if it is 3 by 3 2, if you can reach the last row at 0 0 1, you can always subtract by multiply with some number and subtract it with the previous columns and make it 0.
Okay.
So if you reached in this form, you can say that it's already a full rank matrix. You don't have to go till last part to make it identity.
Hmm.
Okay,
And
so
this
now,
is
yeah,
this is same for square and rectangle matrix
yeah, yeah,
also,
yeah.
and
Yeah. Rank is defined on all matrices. It's not particular fixed to square matrix. Here we just chose a square matrix example. As we will go in the tutorial, we will see that rank of a matrix is defined for, in general, m by n
all kind of
matrix,
matrix.
all kind of matrices. Only inverse is defined on square.
Okay.
Okay,
Thank
so
you,
we'll
sir.
see more of such examples. Let's look into another example. So what I mean by full rank is when m is equal to n. So and it is equal to the values too. So here it is 2 by 2 and it is equal to 2, hence it's a full rank matrix. Okay, let's look into this example. Can someone tell me if this A matrix is a full rank matrix or not? Mm, just say something like whether you think that it is a full rank matrix, it is not a full rank matrix.
As the second row we are getting is 0 0, it is not.
True. So let's those who have not been able to see, let's look this into a full formula. You can see that if you multiply the first row with 2 and subtract it with the second row, it will become 2 and this will become 4. And if you subtract with the second row, it will both will become 0 0. And the A prime will be 1, 2 and 0 0. Now you can never be able to reduce this into an identity matrix. How will you reduce this value to 0 and this 0 will suddenly become 1? There is no operation, row column operation that you can do to make the 0 1. Right? Hence, A is a rank 1 matrix because only one of the rows is actually non-zero, the other is fully zero, and is not a full rank. Does it make sense?
Yes, sir.
Okay, so let's move ahead. Now, why are we studying rank suddenly? The rank is important. So when you have a matrix equation Ax equals to B form, if it's a full rank matrix, it will have a unique solution. If it is not a full rank matrix, then it can have either infinite solutions or no solution. Remember the case where you have a singular Ax equals to B, small x is equal to B. When A was 0, you had two cases whether it can be infinite solution or no solution. Here, the full rank is the one that defines whether it will have a unique solution, in no solution or infinite solutions. So A equal to 0 there now is your rank definition here. Okay, now let's look into each of these questions sequentially. So why a full rank has a unique solution? Let's look into this equation first. Remember this equation that we went through before, Ax equal to B, we did this Gauss elimination operation. We have 2, 3, 8 and 1 minus 1, 8. This is the equation and this is how we were performing the equations, right? Yeah, everyone remembers this part, right?
Yes, sir.
Okay, so the interesting part will come now. The one that we were looking at, A needs to be a full rank matrix. This part we are calling it A, and this 8, 8 we are calling it as B, right? Now, if you look at this equation, after doing row operations on it, we were able to reduce it into this form. This form, we can convert this form into an identity form, right? You will feel like, how can this form be created? You can multiply the first row with 0 and multiply the second row with 1 by 5 and add both of them.
You will get one hair and it will become zero hair. And then similarly, you can do the same thing to make one hair and zero hair. You simply multiply. You can see that, right? You can convert this into an identity matrix by some row operation, right? Now the swapping is also allowed. You can swap these two rows and the equation still remains the same. So you can convert this into an identity matrix form, and hence you can always find a unique solution. In this case, the unique solution is x is equals to 32 by 5, and y you can simply calculate by putting the value of x here, and you calculate the value of y. So you can see that if a matrix A can be converted into an a full rank matrix, if A is a full rank matrix, there is always a unique solution there. Can everyone see that if A is a full rank matrix, you can always find a solution? So if you are still not clear how can we convert into an identity matrix, think in this form. Let me give you another way of seeing this thing. This matrix is representing this equation, right? There is no reason why we can't put 5x minus 0 equals to 32 as first equation, and second equation as 2x plus 3y equals to 8. If we write 5x plus 0y equals to 32, then it will become 5, 0, 32, and the second equation will become 2, 3, and 8. Hence, now you can see 5, 0 is there. Now 2, 32, 2, 3 is there, so you can just simply make this element 0 and then it will become an identity. I will wait for a while here to make sure that everyone is following this part. So if you want me to write, I can write. If there are any doubts that this matrix A, how is this matrix A can be converted into an identity matrix, I can write and assure it will become an identity. If anyone still has doubt, or if it is clear, then we will move forward. Okay, nice. No one has. So no, everyone is able to see that this can be created into identity matrix, right? Okay, so this part is, I'm assuming that this part is clear. So if A is a full rank matrix, there will always be a unique solution. Now let's say look into when A is not a full rank matrix, and when is the case when it will have no solution. Can someone see what is this is this matrix? How many solutions does this matrix have? So we can see that we can write this equation, right? It is 2x plus 2y is equals to 8, minus x plus minus y is equal to 8. This is the equation. Does this, what is the value of x in this case? Let's see the calculations first. So if we simply perform 2 times the row 2, and then when we add these two, it will be 2x plus 2y equal to 8 and 0y equal to 24. You can see that 0 equal to 24 is a contradiction, and hence, first of all, this A matrix is not a full rank matrix, and hence there is no solution because 0 cannot be equal to 24. And hence, this equation does not have any solution. So does it make sense?
Yes. Yes, sir.
Okay, so let's look into, so when the A is not a full rank matrix, we saw a case when it will have no solution. Now let's look into a case when will it have many solutions. Okay, so now consider this operation when 2x plus 2y equals to 8 minus x minus y is equals to minus 4. Now if we do this operation 2 times 2x and it becomes this, and now when we add these two rows, it will become 2x plus 2y equals to 8 and 0x plus 0y equal to 0. Now from here, can we say that there are infinite solution? Infinite, not just not just one or two solutions. There are infinitely many solutions. Many solutions. Can someone can you see that from this equation we have many solutions? So let's simplify it further. This equation, what is this equation? If you write it in a equation form, it's simply x plus y equal to 4, right? You can simply divide by 2 and we get x plus y equal to 4. Now this equation can have many solutions. The solutions can be 0, 4. You put 0 x equal to 0, y equal to 4. It is correct. If you put x equal to 4, y equal to 0, it is still correct. You put x equals to 1, y equal to 3, it is still 4, and such and many such things. And hence you have infinitely many solutions. So even when the rank is not a full, A is not a full rank matrix, you can still have infinitely many solutions. Why? Simply because it becomes 0 equal to 0 case. I will wait for a while to see if this part is okay. So is this part okay? Okay. So here we will stop now. If there are any other questions that needs to be addressed, I can take questions now, and then we will move into tutorial section now. So if there are any other questions in today's lecture. Okay. So if there are no further questions, then we will now move into tutorial section. So is is this visible? Is the font size sufficiently large enough, or should I increase the font size?
So please increase a bit.
Okay. Is this better? I don't know. This became too big though. This is okay.
Yes.
Okay. So let's start. So you in the previous lectures you must have been introduced with NumPy. So we will be working with NumPy again. So we have array. Say for example, now we can make matrix A, which is 10 minus 1 0 0 4 2 6 minus 6. So this matrix looks like this: 10 minus 1 0 0 4 2 6 minus 6. The shape. Okay, so this interesting part is. So can someone say what is the shape of this matrix? Though you have already seen it. So what is the shape of this matrix? What is the matrix size? When I mean shape, it means what is the size of this matrix? What is the value of M? What is the value of N?
4 cross 2.
2 cross 2.
Let's see whether it is 4 cross 2 or 2 cross 4. It's actually 2 cross 4.
Okay.
Why? You have 2 rows and 4 columns. So the correct answer is 2 cross 4. Now, okay. So now we have also seen transpose operation. Remember the transpose operation where we change the rows and column values. So now if you perform A transpose, which is just reshaping the matrix to 2 cross 4 will become 4 cross 2, and the matrix looks like this. So what we did was we just took this value. Oh, this is actually a very different. This is not the reshaping. This is a very complicated operation. I don't know why the operation is there. Okay, let's just do transpose operation. So let's look at into this. So this is a transpose operation. What it does is that it takes this row and makes it into a column. So if you don't remember the transpose operation, let me go back to this slide of transpose operation once. So the transpose operation looks like this. You take the row and it becomes a column. If you take if you take a column, it becomes a row. If you take a row, it becomes a column. And if in a matrix case, row will become a column. Every row will become one column. Okay. And if you try to transpose this, every again, if you take this row, 516 will become a column, which is 516. So A transpose is what?
A.
You can see, right? A transpose is A. So here, if you do this A transpose operation, so all the rows that were there, 10 minus 1 0 0, the row became column. 4 2 6 minus 6 become 4 2 6 minus 6, a column. Now let's look into A transpose. Now, how many of you think that it will become A? Now, if everyone thinks, then you can stay silent. Because okay, so let's see. A transpose is actually equal to A. So you see that the values are exactly the same. Make sense? So the transpose operation is as many times. If you apply even number times, it's actually the same. A transpose. Let's just
Sir,
what is, yeah.
is this T is a readily available function or is the
Yeah,
user
it is.
defined?
No. It's a available function. I'm not defining anything. It's in
Okay.
NumPy array. It's already defined. So
All
what
right.
will be the value of this?
Again, the
This is
4 rows
equal
and
to
2 columns.
4.
A
It's a,
transpose.
this is A transpose, right? Okay.
Yeah.
So this is A transpose. So I think you got the point that how a transpose operation works. Now let's look into how do we select element in a Python program. So if you have A and you want to select 1 comma 2, so let's first see what it is before printing anything. So okay, let me just remove this transpose here so that we can see what is. So what is the value of A 1 comma 2?
-1.
Okay. So in this case, I understand what was the confusion though. In this case, we actually start not from 1, we start from 0, 1. This is how we read. So this is row number 0, this is row number 1. This is column number 0, 10 4 is column number 0, minus 1, 2 is column number 1, and that's how we read. Now, can you tell me what is 1 comma 2 again?
6.
Yeah. So let's see. The correct answer is 6. It's row 1 and column 2, so which is row 1 and column number 2, 0 1 2, which is 6. Okay. Now, if we change the value of 1 comma 2 to 10, we can do this thing now. Okay. So this is how it will become. So now let's print the new value of A. So if you see, the 1 comma 2 initially was 6, now it has become 10. So this is how you can change the value of any element in the array. Okay. Okay. So let's move ahead with the next part. So now this is a random number generator. So this becomes a very important element. Just know this part. Where you will use it will come. It will become handy in the coming lectures. Just know this thing that if you want to create a random integer between 0 to 10, I mean random, literally random, between 0 to 10 of size 5, you can say 2, 5, 6, 7, 9, 8, anything, right? Between 0 to 10. So it will just create a random integer between 0 to 9. It's not 10, but between 0 to 9. And it will create three random numbers. And if you want to create a random number between 0 and 1, here it is rand int, you call random, and it will create a size 3 random number. So let's look into this, and this is how you do. So if you want to create 15 random numbers of size, so let's just first stop this. So if you want to just create 15 random numbers, you see you have got this 15 random numbers. Yes, random integer, sorry, not random number. Now, if you want to create a random number between 0 and 1, and you just don't want to create one, you want to create only 10 random such numbers, and there you go. You have 10 such random numbers between 0 and 1. So where we will use this, it will come handy. Even if currently it is not clear why are we studying this, but it will become handy as we see in the future tutorials, not in this tutorial, but in future tutorials. Okay, now the most interesting part. Let's do rank calculation using Gauss elimination. Now, since everyone is familiar with what Gauss elimination is, we'll take this big example now. Three equations, three unknown with this complicated numbers, and not so complicated numbers. And we will do Gaussian elimination, and we'll see whether the rank is full rank or not. So let's convert this equations into a matrix. So we write matrix A in this form. So how many of you can see that this matrix is, can everyone see that this matrix A is a representation of this matrix? This equation.
Yes.
You can see?
Yes.
But there are only three equations and three unknowns. Why is there four variables here? Shouldn't the matrix A be a square matrix, like 3 cross 3 matrix? What is this fourth element?
The last one of every equation,
Yes.
the 318 and -2.
Yeah, this is exactly what 318 and -2 are. There was a reason that we wrote our equations in this form. There was a reason that I wrote A and B very together with each other. The reason was very simple, that whatever operations that you perform, or a row operation that you perform, you also perform the same row operation on the B itself too. This is, you perform a row operation on A, you also perform the same operation on B too. It's not just that you individually you only perform on A. It's not the case. You also perform the same operation on B too. That's why I wrote it in this form. So it is easier when you write the entire equation Ax equal to B in just a matrix A, which is this long matrix. Which is what is the size of this matrix?
3 cross 4.
Yeah, 3 cross 4. So there. So now you can see the matrix A is only this 3 by 3 matrix, and the B matrix is 3, 18, and -2. Now we will be performing row operations on this, and if this matrix, this 3 by 3 matrix, if you cannot convert this matrix into an identity matrix, then this will have no solution. It can have no solution, it can have infinite solution, but it will not have a unique solution. Okay, now let's look into this thing. So we will define some of the functions like this. So this is row swapping. Remember that even if I change this equation, say for example, let me just change something, and you tell me whether this is still okay or not. If I just define this, is this A correct? Is this matrix A correct? Look at this matrix A, and this is the equation. Is this matrix correct?
Yes.
You can see that this matrix is correct. This second equation is 4x plus 2y minus 3x3 is equal to -2, but it is at the last. I just ended up putting it the second. Is this still correct?
So did we mention any order in which we have to write? I didn't recall. Is there any rule in which we have to write the equations as a matrix?
Yeah, true. So there is no such rule, and you can see that why will there be such rule? You can always put this equation in the second place, or this equation at the last place, or the first equation at the second place. It does not matter, right? It will still have, if it has to have a unique solution, it will always have the same solution,
Hmm.
right? So by changing the row position, you're not changing the solution. True? I can just put this way. This
Right.
form two, and I'm still not changing the equation, right? Now tell me this. Now I'm going to do something interesting. Now tell me, is this equation the same equation?
If you're doing one operation with one row, then it should be done with all.
Maybe I'm just asking you. First, see whether this is the correct equation. Does this matrix represents the same equation? I will tell you the answer. I'm asking the same question though.
No, but like
So
what I refer is in the Gauss elimination, the whatever multiplier we are choosing, we were applying it to all the equations.
yeah, no, not all the equations. Let me go back there. We all multiplied 3 with row 2, so we multiplied 3 in
Ah,
all
yes,
the
yes,
elements in
yes.
the row, not in
Okay.
the above equation.
Yes.
So
We were choosing a one common multiplier so that we can subtract and reduce the unknown values and
true, true, true.
okay.
Completely true. So tell me, is this equation, the matrix that we chose here, the root here, does it represent the same equation?
Then it should be yes.
Yeah.
Yes, sir.
You can see, right? First, I did the swapping, row swapping. The last equation became the first equation, and the second equation becomes the last equation. And I just multiplied the first equation with 2. And it is 2x1 minus 2x2 plus 2x3 is equals to 6, which is exactly the same. Just divide by 2 and this equation is the same. So everyone is able to follow this part, right? Swapping rows does not change the equation. Multiplying does not change the equation. Now tell me, this is what I'm going to do now. This is something very interesting. Wait a sec. Now tell me whether this is acceptable. Is this to represent the same equation?
I'm not getting how the 7 is there.
Oh, okay. I first multiplied the first equation with 2
Three,
and
three,
added
huh.
1. Now tell me whether this 2 represents the same set of equations.
Yes, sir.
Anyone else?
I think it's not.
Can someone also respond? Someone else? I want to see other responses too. How many of you think that it represents the same equation? Let's see how many hand raises was yours. So please raise your hand if you think that both these equations is exactly the same.
Sir, the answer is yes, sir.
The answer. So you are also changing the that it is same.
Sir, you said that you multiplied it with 2 and you added 1.
So the equations are exactly same.
Yes, sir.
Okay. So anyone now have other opinion that they are not same? Any contradictory? Anyone who says that it is not same? Everyone is clear that it is same. So I'm assuming everyone thinks that it's the same equation, right? Okay. The answer is that they are not same equations. Okay. So let's look into this thing. So this is clear that the first row represents the second equation, last equation, and the second last equation represents the second equation. This part is clear, right? These two equations. The only
Yes.
confusion is in the whether the second equation represents the same equation or not. Let's write this equation. It's 3x. Okay, let's just see. This is 3x1 minus 3x2 plus 3x3 is equal to 7. Now, if you divide everything by 3, let's divide everything by 3, it becomes 7 by 3. Now, do you see that this equation and this equation is entirely different?
Yes, sir.
So, definitely this equation is not equal to this equation, and hence this matrix is representing something else, some other equations there. Make sense?
Yes, sir.
Okay, so what operation was not allowed? The operation of addition is not allowed. So you cannot add randomly 1 anywhere. 1 to any scalar value you cannot add. So if I make it like 4 minus 4, so I added 2 now, right? This is also not allowed. I added plus 2 here, right? Multiplied by 2 and then added 2 to every element, it becomes this. So this is all not allowed. Addition is not allowed. Only multiplication and swapping is allowed. Addition is not allowed.
Okay, sir.
Make sense? Okay, so now we are back to the same equations. I have gone back to 2 minus 2 to 6. So let's just go back to the original form though. So this was the first equation, this was the second, and this is the last one. Just take this one. So this is the same equation again, the same format equation. So everything is same now. So we did all form of random experiments here. Now we will just look into each of these equations. So row swapping is if we want to swap k and l rows, which is actually a good operation. We can do such thing in Gauss elimination. So this is simply swapping. You create a temporary variable b, temporary variable. You store all the elements in b, and you start swapping each element in I and j. Everyone is familiar with Python, or do I have to go through this for loop to explain this part? Everyone is familiar with Python?
No, sir. Please explain.
Okay. Okay. So let's look into this. So you have a shape. So you calculate the shape of the which is m, zeroth part, and then you have shape of 1 is n. So m number of rows, n number of columns. So we first copy it into a matrix B. So we copy np dot copy A. So it will create a B matrix. It's a copy of this A matrix. Now we want to swap rows, right? So the number, we will go with each of the elements in the column. So we first take the kth. So we want to swap the kth row. So we take the kth row and the 0th column element, keep it in the temporary variable, and when choose the kth row and the jth column and replace it with the lth row's jth column. So we are still now swapping the variable, the row k and l. We swap the kth row with the lth column, column's jth element, and the lth row and jth column element is swapped with the temporary variable that you have stored before. I suggest that currently, because we have limited time, I suggest that you actually look into this for loop. I will show some of the operations below. If this part is still not clear, I will have another class during the after 2 lectures again. And if this part is still not clear after going multiple times with yourself, then I will explain this part again. But I have currently limited time. So please trust that this will perform this row swapping. You have to check this by yourself for a while once. Okay, so scaling is very simple. You just multiply each element, each column with that scale number. Whatever scale that you want, scale is a float number, and you can multiply each of these elements with that scale. Adding 2 rows where you have k and l and a scalar, though scalar is not allowed. Scale the value of k, scale the value of row. So you want to scale the value of row by k and then you perform addition. So you perform scale and then you add the element in the lth row. So it is like k times the scale. The row k will be multiplied with the scale, and you want to add it with the lth row. Okay. Now let's look into some of these operations now. Let's just stop here. So we have A. We need to first print A. Let's print A first. Print A. Let's look into each of these operations first. What happened? Oh, sorry. So you have A, which is this a matrix, and you want to swap the rows 0 and row 2 are swapped. Row 0 is this one, and row 2 is this one. Can you see that these two rows have been swapped?
Yes, sir.
Yes.
Okay, so this is what swapping does, that you want to swap these two rows, and this is allowed in Gauss elimination. As we see, it just does not change there is no ordering in the equation, so we can do swapping as many times as we want. Okay, so this part is okay. So row swapping we did. Now we will switch on this one, scaling. So we will scale and see. So row scale is that we want to scale the first row with scale 2. So you have this first row. First row is this one. So first row is this one, and you want to scale it by 2. So you will multiply 2 with everything. Can you see this part?
Yes, sir.
So you are multiplying row 1 with 2. So you just multiplied every value there. Now let's see this part. So what you want to do here is that you want to first, okay, we will see. Let's just do this thing. So here, what we want to do is that we want to 3 times the row 0, and then we want to add it to row 2. So you first do 3 times of this. Let's just first take the first element. So you multiply with 3, it becomes 3, and then you add it to the last row. So 3 plus 4 is 7. You take multiply by 3, it becomes minus 3, and you add it with 2, it becomes minus 1. 2 minus 3 is minus 1. You multiply by 3, 1, and you add it to the last row, it becomes 0. You multiply by 3, 9 minus 2 is 7. Is it okay? This part is okay, right?
Yes.
What will this do? So it will simply just add the last two operations. So it will take the first row, scale it with 1, which is like simply multiplying 1 everywhere, and then just add it with this element, right? So 4 plus 1, 5, minus 1 plus 2 is 1, 1 minus 3 is minus 2, 3 minus 2 is 1. Okay, you just simply take this, multiply with 1, and add it here. So this is what it becomes. Okay, so this is now row addition with scaling. So you want to multiply, you want to add it with second row, multiply the first row with 3. So this is what it is. I think you once you go with these equations by yourself, I think you will be able to follow what is happening there. So yeah, so there you go. This
So
part
what
is
is the
right.
default scaling value if you are not specifying?
Okay, the default is not set though. You need to set. You can set the default. You can set. So let's just set default is 1. I set it as 1 now. So now
But
even if,
anyhow, anywhere we have to specify that, right?
no. I now just made it like now just set the default as 1 here in the definition itself.
Okay.
So now I just set the definition as 1. So now you will, if you add 0 and 2, it will simply just add these two rows.
Okay. And but then whenever we want, we can mention the argument and it will take it dynamically. Not as
Yeah. If you want to do 3 again, it will take
Yeah.
the same thing. It will make it 7. But if you don't, if you just remove this, since I made the argument default as 1, now simply it's add, right?
Okay.
Now if you make it 3 again, so you can see that it's now just multiplying this over with 3 and then adding with this element to get this value. Okay, so now let's go and perform our complicated Gauss elimination method. Given that we have already crossed the time, I will just perform this. I assume that they are doing some row scaling and everything. So we'll just look into the what is the value that they are doing. So they first did, they multiplied with -2 the first row and added it with row 1. So let's multiply with okay, we need a again to see what they are multiplying. Print a. So this is your a matrix. So they multiplied with -2 and added it with first row. Multiply with -2, added with first row. So if you multiply with -2, you can see that it becomes 0. -2 is 2, and you add it with 1, it becomes 3, and similarly the other values, right? So they first were able to reduce this into 0. Good, we are able to. Now how will they make it reduce this element to 0? So they must have multiplied with 4 here and then subtracted with the last row. So let's look at what they did. So they multiplied -4 and then added it. Okay, so let's, since they do not have subtraction, so they multiply with -4 is this and then add it to this element. So -4 and -4 plus 4 is 0. -4 plus 2, -4 into -1 is 4, plus 2 is 6, and similarly the other value. -4 plus -3 is -7, -4 is a 12, -12, and -2 is -14. Okay, so this part is the same. Now what will they do here? Now they multiplied the row 1 by 1 by 3. Okay, row 1. So this is 0, 1. They multiplied everything by 1 by 3, which is completely possible. You can do such thing. So which is 1, 2, and 3. So if you multiply 1 by 3, it becomes 1. 6 divided by 3 becomes 2. And 12 divided by 3 becomes 4. Remember why we can do this multiplication by 1 by 3? We can do such thing. Let's go above. By the same logic, if I scale everything by the same number, and the equation still remained the same, right? This equation and this equation is exactly the same. You can just simply multiply by 2, the equation does not change. So simply multiplying by 1 by 3 also does not change. Make sense? That's why they can multiply by 1 by 3 and the equation still does not change. This equation, if you multiply by 1 by 3, the equation still remains the same. Now what they did was, in the last, they multiplied by, okay, so they did not just multiply by 1 by 3, they also actually added it with the last element. So they multiplied by 3 and then added with, multiplied by 6 and then added to it. Oh, no. Let's see. So they multiplied by 1 by 3 and then add with the second row. So they multiplied the second row by 1 by 3 and then added with this element. Is this what they did? No, I don't think this operation is incorrect though. They are not doing that thing. I see. So they first did one and second row is multiplied by -2. So here they multiplied with -2 and then added with it. So it becomes -6 and it becomes 0. -2 if you do. So 6 2 is 12 and -7 becomes -19. -24 -14 becomes -38. So they multiplied with -2 and then added with the last element. So last element also becomes, this also becomes 0. And then after that, they actually multiplied everything by 1 by 3. So it becomes 1, 2, and 4. So now you see that this first A matrix itself, if you divide the last element by -1 by 19, this becomes an almost close to identity matrix, right? You can now, once it converts into this, you can always make this matrix A matrix into an identity matrix, right? If you're not able, if by some chance because of my uh, presentation or if I got confused in between, if you're not able to follow that how it became identity, it will eventually reduce into this matrix if you go through this again. And now from here you can actually reduce into an identity matrix. So A is a full rank matrix, and hence there is a unique solution. Oh, I have already crossed that time though. So now we can actually calculate the A matrix directly. So you can just ask, there is an inbuilt function called matrix rank, and if you ask the rank of the matrix, it will say 3, and that's what the rank is. 3 by 3 has a full rank of 3. And now you can solve Ax equal to y. So now you have a 3 by 3 matrix, and y is 2, 5, and 3 as previously. It used to be 3 by 3 and this matrix. And now if you solve, the solution is this value. There is an inbuilt solution that you can do. And the other solution was, remember the other solution that we had, A inverse B. The solution x is equals to A inverse B. So you take this A matrix, 3 by 3 matrix, calculate the inverse equation, inverse of it. So there is an inbuilt function here, and then simply multiply A inverse y. Ax equals to y is equals to A inverse y, and then if you calculate print x, it's exactly the same solution. So either you solve through some inbuilt package or you calculate A inverse times y is the same solution. And this part, I will think I should leave now. I should stop though. Or is it okay if I continue? I think okay. I think I should stop because this has become too much for today to consume. Maybe when my next lecture will come, these things will be back again. The next lecture that I will be taking on is dimensionality reduction. So everything that you have studied today will come back again. So we can take there. But I will stop here and I will share this notebook with you. I will let you explore these parts. This is just simply showing that when will it have no solution, large number of solutions, those equations that they are talking about, and that's it. So I will stop here and I will share all the slides and everything now. Give me a few minutes. I will share such everything here. How do I share? So I will share all. And other thing is this. Just a sec. Let me just convert this part, share all the slides and everything with you once. So this is the tutorial notebook, and the other one, the today's slides and everything is here. The PDF thing. So can someone confirm that if they can open this both this file and both these links? Uh, can someone confirm that if they can open this?
Slide PPT is being open, sir.
Okay, so the other part should also be open. You can also download the Jupyter notebook. You can open those notebooks on Colab. I'm assuming that now you are you since you had your first tutorial, you should be able to do that. And yeah, so please go through this tutorial once again. I think the tutorial was. I think I needed more time for completing the tutorial. But please go through the tutorial and the slides. If you have any doubt, you can ask the same in the next lecture too, or whenever the next lecture happens with me, we will discuss the same then. Thank you again. I again over exceeded the time limit. Thank you for attending the lecture.
Thank you, sir.
Thank you so much. Yeah.
Thank you, sir.